Hi, welcome back to my channel Net Physics, and in this video we shall discuss the questions of CSI Net examinations and all the questions of nuclear physics. So let's start the video. So the first question is from December 2013. So here you can see the question is that the intrinsic electric dipole moment of a nucleus, this. So whenever you are asked about the intrinsic electric dipole moment of a nucleus, then you have to keep in mind that the intrinsic dipole moment of a nucleus, it is always 0. So the correct option is option C. This is directly, you don't have to think much about this question. For intrinsic electric dipole moment of a nucleus, the dipole moment is always 0. Okay, the intrinsic dipole moment. So next, here we are having that according to the shell model, the angular momentum in unit of H large and the parity of the ground state of the nucleus lithium-37 is. So here we are having 4 options and we are asked to find the parity of the ground state of this nucleus according to the shell model. So whenever we are doing questions through the cell model and we are asked to find the parity, in that case first of all we used to see the number of protons and the number of neutrons. So here if you see here 3, this is the number of protons, and the number of neutron is 7 minus 3, that is 4, right? Because this is the total number of protons and neutrons. So here if you see, the number of protons is 3, which is odd, and the number of neutrons is 4, which is even. So we won't write the energy levels for the even number, and we will write it only for the odd number, and which is as such. So here what you will see, so here the spin is 3 by 2. Parity is formula is minus 1 to the power L. So for P, the value of L is what? 1. So minus 1 to the power 1, it is minus 1. So finally, the parity of the ground state of this nucleus is 3 by 2 negative. So the correct option is option A. So now let's come to the next question. So the next question is from June 2014, and it is said here that the recently discovered Higgs boson at the LHC experiment, it is decaying into a photon and a Z boson. Means we are considering H to be the Higgs boson here, and the Higgs boson is decaying into what? A Z boson and a photon, and the rest masses of the Higgs boson, that is of this H and this Z boson, it is given 125 and 90. So these are the given terms, and the decaying Higgs particle is at rest, and the decaying Higgs particle, it is at rest, and the energy of the photon will be approximately what? So we are asked to find the energy in this particular case. So first of all, we have written the given terms here. We have considered H to be the Higgs boson. This is the reaction which I am showing here. Now what you will see, we will write the formula. E gamma is equals to what? EH square minus EZ square by 2EH, right? So the value of EH is what? 125. And the value of Ez is what? 90. Substituting the value of EH and Ez, and on simplifying you will have 15625 minus 90 square is 8100, and in the denominator multiplying 2 into with the value of EH, which is 125, it will give you 250. Now it will give you 7525 by 250. Cancelling these two terms, you will have 301 by 10, that is approximately equals to 30.1, which is 30 giga electron volt. So this is the energy of the photons. So the correct option is option C. So in this question we will see, in a classical model, a scalar meson with spin 0, it is consisting of a quark and an antiquark, and this quark and antiquark, they are bound by a potential V is equals to AR plus B by R, and the value of A and B is given here. And if the masses of the quark and the antiquark are negligible, then we are asked to find the mass of the meson, right? And here we are having 4 options. So firstly, I would like to say here that these particles in this, they will be at a minimum potential at equilibrium. The difference between, or the separation between the potential of these particles will be minimum at equilibrium. And whenever we are using this equilibrium condition, then what we are using? We are using the condition of maxima or minima. That means we are just differentiating the potential and putting it equals to 0. Okay, this we are doing so that we can get the value of R, because we are asked to find the energy, right? First of all, we will find the value of what? First thing that we will do is we will find the value of R, right? We need to find the mass. This is what we need to find. We will first find the value of R. Why we are finding the value of R, that I am saying you first here, that we will use the uncertainty principle. Delta E, delta T, it is what? Approximately equals to what? H slash. This is the value. This is the formula, right? And from this you will write delta E, it is equals to what? H cut by del T. we know that distance is equals to what? Speed into with time. This is the formula, speed into with time. So here time will be equals to what? Speed by distance by speed. That means what? It will be what? H cut. If you will write distance here and speed here, okay, the distance is here r. Okay, this is the reason we were finding r here. First we will substitute the value of r this here, okay, like that, and then at the end what we will do, we know that E is equals to what? mc square. From this we will get the mass. These are the three steps that we will be doing. So now let's start. First of all, what we will do, we will differentiate the potential. So on differentiating the potential, what you will have? A minus because A is constant and ddr of r is what? 1. Here you are having B is a constant term. 1 by r on differentiating, it will give you what? 1 by r naught square. I have taken r is equals to r naught, right? Now it will give you A is equals to what? Taking this particular term to the right hand side, you will have B by r naught square, and r naught is square is equals to what? B by A, and finally r naught is equals to root over B by A. So here what we will do, we will substitute the value of A and B given in the question. So one thing I would like to say here, whenever you are reading the question, just focus on the units given, because here the value of B, it has Fermi, okay, but in the value of A, it is having Fermi inverse. So this is a very simpler thing which might sometimes lead you to some like silly mistake, I could say. Or so focus on this, and on cancelling this double zeros means 100 and this 200, you will have 1 by 2, and this will give you what? Just Fermi. So r naught is equals to what? 1 by root 2 Fermi. This is the value of r. Now what you will do, we will use the uncertainty principle. According to the uncertainty principle, delta is approximately equals to h slash. That is, delta is equals to approximately h slash by delta. So we know distance is equals to what? Speed into with time. This is what we said. This is a very basic formula. So time will be equals to what? Distance by speed. That is r naught. In the above it will be c. Okay, r naught by c means the speed will go to the numerator. And finally we know that the value of h cut and c is what? 200 mega electron volt Fermi. So I have substituted the value of h slash c and the value of r naught from this particular term, 1 by root 2 Fermi, and this will give us energy delta E is equals to 200 root 2 mega electron volt. So we know that the energy E is equals to what? mc square. That is, delta E is equals to what? mc square, right? So m is equals to what? Delta E by c square. This is the formula for mass that we have found from this, and it will give you, putting the value of delta E here, c square will be as it is, because it is in the question mega electron volt by c square, and root 2 is what? 1.414. So when you will multiply this 200 with 1.414, you will get 282.8 mega electron volt by c square, and this is approximately equals to what? 283 mega electron volt. So the correct option is option B. I have taken it approximately 283 because the option is having 283 here, and rest all other are wrong options. The next question is from December 2014, and here we are having 4 processes. So out of this 4, okay, which of the above is, or we can say are, forbidden for free particle? This is what we have to see. So for this, first of all, we will see the energy conservation, right? If you see here, for the first equation, here the charge is what? 1, for neutron is 0, here also 1, here it is 0. So the charge is finally conserved. If you see the lepton number, it's 0 this side, and here it is, this is minus 1, this is plus 1. Okay, so this is also conserved. And if you see barrier number, it is 1, and this side also it is 1, so it is also conserved. So here you can see all charge, lepton number, barrier number are conserved. In the second one, what you will see here, the charge is not conserved. You can see here, this is 0, this is 1, this is 1, and this is 0. So the charge is not conserved, so you don't have to move further for this. Okay, now then the third reaction, if you see the charge, so it's 1 and 1, the charge is conserved. Lepton number, for this it's 0, for this it's minus 1 and plus 1, so it is conserved. The barrier number also you can see it is conserved, because there is no barrier in this reaction. Now in this one, if you see the last one, the charge is what? 0, because no charge, there is nothing. Okay, this is charge is 0, lepton number is also conserved, and you can see barrier number also conserved. You can see directly, you can see, you don't have to see anything like very, it's not okay. So whenever we are talking about free particle, we have to see the energy conservation, right? And you can see only equation 1 and 2. Okay, only these 2 equations, na, these are violating the energy conservations, not the third and the fourth equation. So The correct option is option D. And one thing I would like to say you, for if you don't remember which are the baryons and which are the leptons, then I would request you that just make a proper chart and remember which are baryons and which are leptons and all these things, okay? Because it is not possible to mention the complete chart in this particular video, so I have just written the heading that what is conserved and what are the terms, okay? That's all. So now let's come to the next question. So here in deep inelastic scattering, electrons are scattered off to protons, okay? To determine if a proton it has internal structure, we have to find the energy of the electron, okay? So the question is that electrons is scattered into protons, and we have to determine that if proton is having internal structure, then for that what should be the energy of the electron, okay? So here we are having four options. Firstly, I would like to say you one thing that if internal structure of proton, okay, is there, or we can say if internal structure of a proton is asked to be determined, we have to keep in mind that the de Broglie wavelength of the incoming electron, okay, it must be equal to, or it must be nearly equal to, you can say, to the radius or the size of the proton. Means lambda must be equals to what? R. And here lambda will be equals to what? 10 to the power minus 15. Now we will find the energy. So we know the energy E is equals to what? hc by lambda. The value of H is what? 6.626 into 10 to the power minus 34, and the value of C is 3 into 10 to the power 8. Lambda is 10 to the power minus 15, and I have divided by 1.6 into 10 to the power minus 19 because I have converted it into electron volt, because in the option the unit is electron volt. Now I am taking these terms in one side, and 10 to the power minus 34 plus 8 plus 15 plus 19, which will give you what? 10 to the power 18. And on calculating this particular term, you will have 12.42, right? And it will give you what? 1.242 into 10 to the power 9. That is approximately equals to 1.25 into 10 to the power 9 electron volt. So the correct option is option A. And this simple calculation you can do it on your own. Now let's come to the next question. In this question, if the binding energy of a nucleus, it is given by this, and the value of AV, AS, A symmetric, AC, it is given. Okay, the values are given. Then for the most stable isobar of a nucleus with A equals to this much, okay, what is the value of what? What is the value of Z? We are asked to find the value of Z here, right? Binding energy is given. The values of AV, AS, asymmetric, AC, all these are given. So for the most stable isobar of a nucleus with A equals to this much, the value of Z is what? So now for this, what you will write, first of all, we know that for the most stable isobar for a nucleus, the binding energy, okay, differentiating the binding energy with respect to Z, it is equals to what? It is equals to 0, right? So this is what we are going to do. We will differentiate the binding energy with respect to Z, and it will give us what? If we will differentiate, these are the constant terms. It will give minus A symmetric. This is 2 into with 2Z minus A. Again differentiating this 2Z, it will give only 2, and A is a constant. Minus this AC by A to the power 1 by 3 is constant. Z square on differentiating will give us 2Z. So finally what you will see, the minus term I am removing and making all the terms positive, and here you will have what? Asymmetric. This is 2 2s are 4. This 2Z minus A by A plus 2AC by 2ACZ by A to the power 1 by 3. So you will put here the value of A equals to 216, asymmetric to be 24, and the value of AC to be 0.75. These are the values that we will put and we will calculate. So now what you will see here, on putting the value of on putting the value of what? This is the value of asymmetric, that is 24, into with 4 into with 2Z minus A is what? 216. This is also the value of A, and here it was the value of AC, it is 0.75, that I have written 75 by 100, and is 2Z by A to the power 1 by 3, that is 216 to the power 1 by 3. Now if you see, cancelling this 24 and 216 9 times, right? I have considered here 9 times. So cancelling it 9 times, and this 4 2Z minus 216 is as it is. So you will get what? 4 by 9 2Z minus 216. This is the first term. In the second term, this 75 and 100 will cancel, and it will give you 3 by 4. Those terms are as it is. 2Z by 6 it will be. It will be 2Z by 6, because 216 is what? 6 cube. So it will give only 6. So here you will have 4 by 9, 2z minus 216 plus 3 by 4 into with what? 2z by 6. Now here you see 3 2s are 6 and 2 will get cancelled, and you will have here only z by 4. The first term is as it is. Now taking the LCM, you will have 8z minus 864 by 9 plus z by 4. Sorry, not taking the LCM. Okay, just multiplying it basically and then taking the LCM. So then after taking the LCM, first multiplying this 4 with this complete term in the bracket, and then taking the LCM will give you 4 into with 8z minus 864 plus 9z by 36 equals to 0, because 9 4 is 36. Okay, this is the basic LCM, so I am not explaining it deeply. You can just see that when you will simplify this one, this 36 will go to the right hand side, and you will have what? 4 is a 32, z minus 4 into with 8 and 64 will give you what? 3 4 5 6 plus 9z, and now 32z plus 9z will give you 41z. 3 4 5 6 will go to the right hand side and the negative sign will be removed. Okay, and hence you will get z is equals to 3 4 5 6 by 41. Now on dividing 3 4 5 6 by 41, you will have 84.29, which is approximately equals to 84. So the correct option is option C. So whenever you're getting questions related to binding energy and you are asked to find the value of Z for the most stable isobar for a nucleus, you have to just differentiate the binding energy with respect to Z and put it equals to 0. And if some values are given, you have to just put and substitute the values and calculate it correctly. And it is very simple, and almost this questions comes for 3.5 marks. Okay, which is a really a good way to score marks using just this basic concept. Now let's come to the next question. The next question is from June 2015. So here it is that the reaction, this is deuterium. Okay, it is giving what? One alpha particle and a pion. It cannot proceed via strong interactions because it violates the conservation of. So this is a reaction in which we are having two deuterium, and it is giving us what? One alpha particle and a pion. So we are asked that the violation of which is not allowing this particular reaction to proceed through strong interactions. Okay, so for this we will see, whenever we are looking for deuterium, we are looking for the angular momentum. Now in case of deuterium, we are looking through the spin. So for the deuterium, the spin is what? 1. For this is 1. So finally you will have what? 0 1 2, right? Now again you will see here what? For alpha particle it is 0, for pion also it is 0, and here you will see what? It is 0. So finally what? Here also we have 0, here also we have 0. That is the angular momentum is conserved. Now if you see the electric charge is also conserved. No, there is no electric charge, so it is conserved. In case of baryon number, it is also conserved. Okay, if you see the baryon number, it is directly conserved. You don't have to calculate so much here. You have to see the isospin. For the deuterium, the isospin is what? 0. Okay, so it is 0 0. For the alpha particle it's 0, and for the pion it's 1. So you can see here the isospin is what? Not conserved. So what is the conservation that it is violated? It is the conservation of isospin which is violated by this particular reaction, and so it cannot proceed to strong interactions. Now let's come to the next question. So the next question is that here we are asked to approximate the nuclear potential in the cell model by a three-dimensional isotropic harmonic oscillator, and it is said that since the lowest two energy levels, they are having angular momentum L equals to 0 and L is equals to 1 respectively. So out of this two nuclei, okay, we have to find which of this following nuclei it is having magic numbers of photons and neutrons. You have to just check which nuclei is having magic numbers of photons and neutrons. So first of all, you will see magic numbers of what? 2, 8, 20, 28, 50, 82, 126. Okay, so for the first one we will check the number of proton and the number of neutron. So the number of proton is here what? 2, and the number of neutron is also what? 2. So this is what? Magic number. And for the other one we will say 16 and 8. So here the number of proton is 8, so which is a magic number, and the number of neutron is 16 minus 8, which is also a what? Magic number. So very clearly we can see that the option A is the nuclei which have magic number of photons and neutrons, right? So this is very simple, because here only the photons and neutrons are magic numbers. So you don't have to go for the rest one. If you wish, you can calculate, but I have not calculated here because I have got the correct option, the first one only. Now let's come to the next question, which is the last question of this video. So here it is said that the charm quark, it is assigning a charm quantum number C equals to 1. So we have to just say how the Gell-Mann-Nystrom formula for electric charge can be modified for 4 flavors of quark. So it is very simple. The basic formula is I3 plus half B plus S, and if a charm clock is assigned, then it will be modified as what? Q is equals to I3 plus half B plus S plus C. So the correct option is what? Option D. You have to just remember the basic one, and we have just added here C. So that's all in this video. If you like my video, then do share with your friends, and if you have any questions, any advices or suggestions, then you can comment me in the comment section. Also, do not forget to hit the bell icon, do subscribe my channel, like, comment, share. That's all. Thank you. Have a good day.